Hello everyone, welcome to Intro to Thermochemistry. So what is thermochemistry? Let's get started right away with that big question. Thermochemistry is the study of energy changes that occur during chemical reactions and also during changes in state. We're going to start this journey by talking about heat flow. Recall from earlier in class that chemical potential energy, that's the energy stored in chemical bonds of a substance, is changing as reactants react and turn into products. So recall that all substances, they have chemical bonds, they're going to have a certain amount of energy stored inside those bonds. During chemical reactions, one substance is turned into another with a different amount of energy. This process is going to release or absorb energy from the surroundings. Big topic of thermochemistry, as you can imagine, is heat. Mathematically, that's going to be represented by a lowercase q. And what heat is in thermochemistry, we're going to use that word to describe energy transferred from one object to another because of a temperature difference between them. And big thing to note here, you probably have already observed this millions of times in your life, but heat always flows from a warmer object to a cooler object. Other things of note to give us context for the rest of thermochemistry is that chemical reactions and physical changes usually involve release or absorbance of heat. Also, we're going to use this vocabulary. A major goal of thermochemistry is to study the flow of heat between the system and its surroundings. So look at this diagram over here. Whenever we talk about one thing that we're paying attention to, that's our system. It is surrounded by the surroundings, that's everything close to it, and everything else too. So we're going to assume between the system and the surroundings, that's everything in the whole universe. And thermochemistry thinks about the energy exchange between them in the form of heat. As already noted, some reactions release heat and some absorb heat. So let's explore that idea with exothermic and endothermic processes. Exothermic and endothermic reactions rely on this idea of law of conservation of energy. So that might be turning on a light bulb. It might be reminding you of law of conservation of mass, which you've heard of many times. The law of conservation of energy is similar to that. It states that in any chemical or physical process, energy is not created or destroyed. And then as we talk about these examples, keep in mind that heat flow is always given from the point of view of the system, so the thing that we're worried about. Let's start by talking about an endothermic process. Endothermic, it kind of sounds like in, so heat comes into an endothermic system. That means that the system gains heat as the surroundings cool down. So let's look at this example. We have the man sitting by the fire. So heat is coming from the surroundings and going into the system, the man. So our system is gaining heat because the surroundings are losing heat. When we do calculations, and remember that lowercase q represents heat, because heat goes into our system, these are going to have positive q values. Any endothermic process will have a positive q value. Opposite of endothermic is an exothermic process. This sounds like heat exits. So exothermic process, heat exits the system. So the system loses heat to the surroundings. In this example, we have our runner, our system, that is losing heat through the evaporation of sweat. Because the system is losing heat, when we do our calculations, we have a negative Q. We have a negative heat value. Let's explore those same ideas through some diagrams. So this first one shows exactly what we were talking about. That endothermic process, we have the heat going in. Endo, in. Exothermic processes, those produce heat. They give heat off to their surroundings, just like this fire here. Combustion is a great example of an exothermic process. Let's take a quick look at energy level diagrams. First, we're going to look at the one on the left, which is an exothermic reaction, so we know energy will be released, just like in our combustion reactions. So let's take a look at this. We see here that we have reactants and this big bump that comes down. That is the reaction itself. And over here we have products, so the reaction has already happened. So we can interpret the x-axis as time during the reaction, and then the y-axis is the amount of potential energy, or chemical potential energy. In an exothermic reaction, we see that the reactants have a lot of potential energy and the products have less. So when the reaction occurs, we're going to end up having less energy in our compound, whatever it is, than we started with. And that change in energy is energy that's released. So that explains where our exothermic energy comes from. On the flip side, we can see an endothermic reaction. The curve looks almost like a mirror image, where reactants in this case have low potential energy. They go through a reaction and they produce products that have a higher potential energy. That difference, that positive difference, is energy that has to be absorbed from the environment. So that's how endothermic reactions require that energy to come in. Excellent. So let's go back a couple. And we got one more topic to talk about. That's measuring heat flow and our units. They're calories, and joules. So measuring heat flow, we have to use different units than just temperature. So there are two common units. One's the joule. That's your standard SI unit for energy. And then the other one's the calorie with a little c. So 1 calorie is defined as the energy required to raise the temperature of 1 gram or 1 milliliter of water by 1 degree Celsius. This is a useful conversion factor that you'll see quite a bit. 1 calorie is equal to 4.184 joules. We got one more unit that's familiar to all of us, and that's a food calorie. Calorie with a capital C. And that's actually equal to a kilocalorie. So 1,000 calories with a little c equals 1 kilocalorie equals 1 calorie with a capital C. And that's what we use on our nutrition labels in the United States. And so just kind of a fun thing to note if you're traveling or if you're looking at food that's marketed to people mostly from another country, is that our nutrition labels, they use calories, that capital C. If you go somewhere else, this is a UK Kit Kat, you'll see their nutrition is labeled as kilocalories or also in kilojoules. So that's the new content for today. We're going to switch over and look at some practice problems now. So practice problem 1, kind of connecting back to endothermic and exothermic processes. We've got, I'll read it out for you. On a sunny winter day, the snow on a rooftop begins to melt. As the melting water drips from the roof, it refreezes into icicles. Describe the direction of heat flow as the water freezes. So is this process endothermic or exothermic? Take a look, read over those recall statements, and answer the question. Excellent. Now let's move on to another related practice problem. So we got practice problem number 2. This is about paraffin wax. Maybe you've seen it in these blocks and you've used it for canning. If you've ever gotten a fancy pedicure or manicure, this is also the wax they used for that. So practice problem number 2 reads, a container of melted paraffin wax is allowed to stand at room temperature until the wax solidifies. What is the direction of heat flow as the liquid wax solidifies? Is this process exothermic or endothermic? With that, thanks for watching, and I hope you all are having a great day. And as always, please reach out with any questions.